We are ready to start again for the second section of this afternoon. From field detection to disease dynamics, that will be chaired by Stephen Parnell, University of Salford. Okay.
Thank you. Okay, good afternoon, everybody. Welcome to the final session of talks for today before the poster session this evening. We're going to move now from detection and identification, and we're going to go from field detection to disease dynamics. I think it's interesting that these two topics are linked. Disease dynamics tells us something about when and where we can expect disease to occur, and we can use that we ought to be able to use that to target where we put our field detection. So our first speaker is Pablo Zarco-Tejada from the Joint Research Centre for the European Commission.
Okay, thanks very much. It's a pleasure to be here and to talk about the detection of Xylella fastidiosa with hyperspectral remote sensing. And I would like to show the results and from the methodological, technical point of view regarding the flights and the field campaigns that we've been doing in Puglia in the last couple of years. Before I start, I would like to discuss a bit about some terms and some aspects related to the concept of symptoms in the context of remote sensing. And to do that, I grabbed one of the schematic views in one of the latest papers by Almeida from last year, in which it talks about the different phases from the inoculation until symptoms are present. And in order to understand the context in which I show in the remote sensing that we have conducted as part of Puglia project in Xylella fastidiosa, I'd like to say that the reason why Maria Saponari yesterday talked about roughly 12 to 14 months between inoculation and the symptoms have been detected is because we were talking in that case about visual symptoms. And this is what plant pathologists in general talk in the terms of symptomatic. When we use remote sensing, we feel that there is a gap that can be filled in order to detect these symptoms earlier. And this is what we are calling pre-visual detection of symptoms, because the sooner we can detect that there is an anomaly or there is something that is happening to the plant material, then the easiest will be also to take decisions. So the remote sensing that we do is focused on this part here, which tries to detect it as early as possible. Remote sensing, depending on the community in which I present this type of slides, is regarded as spatial remote sensing, because for many people, remote sensing means looking at many different objects, trees in this case, from the distance, and looking at the spatial variability of the area. In this field, we see some trees which are visually affected, some others are visually healthy. But the actual value of remote sensing and the hyperspectral remote sensing that we do in the context of stress detection and early detection of diseases is more spectral than spatial. I mean, it's both, but the actual value is that we have a third dimension that for us is the electromagnetic spectrum, is the fact that every single pixel on the image and every single object here, an object for us is a tree, is actually being detected in different spectral regions, in different wavelengths of the electromagnetic region. So by doing these hyperspectral or imaging spectroscopy approaches, then we are now facing into what is called physiology-based remote sensing, because by obtaining more information in the electromagnetic spectrum, then we can try to assess the physiology of the vegetation. In order to do that and to go into the physiology, we have to understand also the photon-vegetation interactions and the energy budget. It's well known by everyone that most of the light that comes and is absorbed by pigments, it's used for photosynthesis. This is not new. And part of the energy is actually transmitted and lost. Well, it's not lost, it's actually transmitted and multiple scattering occurring to the light, and other leaves will use it. This depends on the scattering of the canopy and the density of the canopy. Another pathway is the reflectance, it's the amount of energy that is reflected in that spectral region. And this is the radiation that we measure when we deal with or we use instrumentation in the laboratory to measure the leaf optical properties of the leaf materials. But the leaf optical properties are the reflectance and the transmittance, and by doing that and through non-destructive methods, we can quantify how much of specific biochemical constituents we have in the leaves that we have measured. But not only in the laboratory, but also in the field. When we are in the field collecting or measuring the leaf optical properties, these measurements in different wavelengths are later used to infer physiology-based constituents, or what I will define later as plant traits. The radiation that is reflected in different wavelengths is like that due to two different reasons. One is the scattering of the medium, I mean how the thickness of the leaf and the characteristics of the leaves. But most important for us is the actual biochemical constituents that we have in the leaves. In principle, anything that absorbs radiation can be quantified, can be estimated by using these approaches. And in particular, and in the context of this project, there are specific biochemical constituents. Some of them are photosynthetic and non-photosynthetic that could be of interest to retrieve from the distance and by using imaging spectroscopy. So some of them are chlorophylls, coranoids, and anthracyanins. If we go to longer wavelengths, we can even quantify from the distance water content, dry matter content, and even other constituents like cellulose and so on. This is not the only one. This is one of the ways we can get into the physiology of the leaves or the plants. Another one that is closely linked with photosynthesis is chlorophyll fluorescence. We are talking about a very small amount. We are talking about around 2% of the amount of energy that is re-emitted at longer wavelengths because it's not needed in the process. And this chlorophyll fluorescence is re-emitted at longer wavelengths, centered at the PS2 and PS1 photosystems. And this small amount, which is roughly about 2%, can be actually retrievable because it's added to the reflectance, to the radiation that we measured from the leaves and at the canopy and from our planes. It's only a 2%, but these 2% tell us something about the photosynthesis because it's what we call the solar-induced fluorescence as another important physiological indicator. It's not only that, also heat, not only through photosynthetic and non-photosynthetic quenching, but also normal plants which are under non-stress conditions due to the exchange of CO2 and H2O. The transpiration makes an evaporative cooling. So under non-stress conditions, any plant that is transpiring will reduce the temperature. Under stomata closure, because there is no evaporative cooling, there is an increase in temperature. This is happening not only in the case of closing stomata, but also in the cases where we have agents or we have diseases that generate a water stress as a symptom. So temperature is also another important indicator. So if from remote sensing we can get at reflectance, chlorophyll fluorescence, and temperature, for every single tree, for example, if we are talking about trees, then we can get into what we call plant functioning. And we can understand, or we can retrieve and assess this plant functioning in the context of in our project, Xylella fastidiosa effects. How do we do that? Well, I'm not going to get into the details, but we have leaf-level physical models that account and simulate the absorption due to different biochemical constituents, and they are from simpler models to more complicated ones. And these leaf models are linked to what we call canopy reflectance models that account for the actual structure of the canopy, because it's not the same to have a turbid medium plane parallel type of canopy than if what we have is, as in the case of olive trees, for example, a pattern of trees which cast shadows, and this has an effect on the actual remote sensing data that we collect. By a scheme that we show here, which is a leaf model that accounts for the biochemistry, and a canopy model that accounts for the architecture, in principle, we can use our images to extract the plant traits, to extract the reflectance, the chlorophyll fluorescence, and so on, and to derive what we call the model-retrieved plant traits. These model-retrieved plant traits, with the current models that we currently have, are chlorophyll content, coronoids, anthocyanins, water content, dry matter content, leaf area index, the leaf inclination distribution function, solar-induced fluorescence, and temperature. But this is not enough. It's not enough because not all the models that we have, especially at the leaf level, simulate correctly the different stress conditions that we have, and specifically the ones happening when we have diseases. For example, it's been a long time ago reported that there is chlorophyll degradation under different conditions. I'm not talking about chlorophyll decrease. I'm talking about actual degradation into different components. And this has an effect also on the leaf level and canopy level type of data that we can collect. And also, we don't have yet in our models correctly simulated other pigment degradations and pigment changes due to xanthophyll cycle, which are linked to epoxidation state of these xanthophylls. So because we don't have these processes and other ones embedded and included already into the models, this is why we need, in addition to the model-based plant trait retrievals, we also need the index-based plant traits. There's a long list of different formulations that are available in the literature, which are linked to any of these other plant traits that I'm talking about. So by using a hybrid approach, this is what we have done in the context of the Xylella fastidiosa project, by linking a model-retrieved plant traits to index-based plant traits in order to account for everything that is happening at the leaf level under our case of Xylella fastidiosa, what we've done is to build linear and non-linear deep and machine learning models, and with the objective and the final aim of flying large areas and applying these models in order to classify and to assess every single tree. Tree by tree physiological assessment. This tree by tree physiological assessment and the actual performance of the different models will depend very much on which spectral band set we have, and this will affect, obviously, which traits will be available. For example, not all the times we can fly a sensor to derive chlorophyll fluorescence. Not all the times we can fly with the correct or optimum spatial resolution a thermal sensor. So depending on the different band sets available and the different data available, the assessment of the different models will change. We have done this approach in the past, not only for Xylella fastidiosa, and for other diseases, using large and medium-sized aircraft, but also using drones. In some cases, we can install the cameras inside the small, lightweight drones that have been used to fly, and in fact, Juan Antonio Navas and myself supervised a PhD on verticillium wilting olive, and we used this type of drones for the acquisition of the images. And we have done it also with large-scale sensors which are very heavy, and you actually need a very big plane to do it. But because of the very fast miniaturization that is happening nowadays, the hyperspectral sensor that you can see here, this was around the year 2000. About 15 years later, this is what we have. No? So, and this is not stopping. I mean, this is probably big. In a couple of years, we'll say that this is too bulky and too big. No? So, in this context of the Xylella fastidiosa project, we have done 2 airborne campaigns in 2016, summer 2016 and summer 2017. At the same time, 5 field campaigns or revisits, 2 of them coincident with the airborne campaigns in 2016 and 2017, flying 3 different sub-areas of 1,200 hectares, monitoring 15 plots of around 4,000 trees per year, with the airborne remote sensing, over 200,000 trees scanned every time, with resolutions ranging between 7 and 60 centimeters, comprising hyperspectral, thermal, and RGB. So, because this is a collaborative project between JRC, that we are coordinating it, but with CNR from Italy and CSIC from Spain, what we've done is to coordinate all the airborne campaigns, but installing the technology from the National Research Council from CSIC in Cordoba in Spain, and with field crew of people collecting data for atmospheric measurements and calibration of data, and for leaf physiological assessments at the leaf level of leaf spectra, chlorophyll, anthocyanins, leaf fluorescence, and other parameters that we measured coincident with the different flights. Just as an example of the type of images that we get at this resolution, this is one of the mosaics obtained by this imaging spectroscopy approach, hyperspectral remote sensing data. We can identify every single tree, but again, the same comment as I said before. When you click on the image, what we have is actually the full electromagnetic spectrum. We get the full spectrum between the visible and the near-infrared for every single tree that is scanned using this technology. This is for hyperspectral, also for thermal. These are typical thermal images that we have collected where we can identify every single tree and retrieve the temperature for every single crown. And by doing object-oriented analysis, we can actually calculate the mean and all the different metrics from the crown level, evaluating and assessing how some of the trees are showing higher temperatures than others, which are one of the traits that we use in our inputs for the modeling. So, in summary, for every single field that we have evaluated and for every single tree that has been assessed in the field, we extract the spectra from the hyperspectral data and the thermal data as well to build the database of what we are calling these plant traits. And these plant traits are used in this hybrid and scheme using the model-based and the index-based approach in order to build the model that I said before using deep learning methods. The results that we've got are at different levels. We have at the index-based trait, at the model retrieved trait, and also in a combination of different traits obtained by this hybrid methodology. If we concentrate on this one, we can see, quite interestingly, that one of the degradation, chlorophyll degradation index is one of the mostly related or sensitive to the separation or differentiation between asymptomatic and symptomatic trees. Thermal-based traits is the second one, anthocyanins, coranoids, and solar-induced fluorescence. These are the 6 best indicators more sensitive to detecting the symptoms of the disease. Because we've done it in 2 years, we could evaluate the robustness, how robust these plant traits are, and compare it between years. So our models, in fact, at the end, what we did was to, through a statistical analysis, use only the indicators that are robust for both years in order to avoid indicators which, for some reason, ambient and other conditions, were robust in 1 year but not in another. The results that we got when we applied this model to the 2 years of data, I'm talking about around 7,000 trees, can be summarized in this slide. This is for support vector machines, this is for neural network, and this is for linear discriminant analysis. Support vector machines are the ones that obtain the best results. And when we use all traits, and when I mean by all traits is including chlorophyll fluorescence, canopy temperature, and all the index-based and model-based traits, we get accuracies of around 82%. If we don't use fluorescence or temperature, we get lower performance, around 80%. But the most interesting result as well is that if instead of using imaging spectroscopy that allow us to get all these plant traits, we use standard methodologies based on RGB and near-infrared, which is in some way the same type of bands that some of our satellites have, or some of the color infrared and RGB cameras have, then the overall accuracy is low, get much lower, and the performance is very low. Not only the overall accuracy, but also the kappa coefficient gets extremely low. Okay, so let's spend a minute with the best results. I'm talking about that we, with 7,000 trees, when we have 2 independent data sets, and we apply to the independent data set, we successfully classify symptomatic versus non-symptomatic at a rate of around 80%. So what happens with the remaining 20%? I mean, why are we failing that 20%? Particularly, I believe that the 80% or 82% is already a good result. But who is failing? Is remote sensing failing? Is the people in the field failing? So we wanted to spend a bit of the time, and what we did was to think a bit about what happens to the trees that remote sensing classified as affected, but pathologists said that they were asymptomatic at the time of the flight. So to evaluate that, what we did was to revisit the same trees over a period of time, over 1 year, for a total of 4 revisits and 1 coincident with the flight, and focusing entirely on the subset of trees that were, as we can call them, the false positives. I mean, those trees that remote sensing said that they were affected, but the pathology said that were not affected. Out of more than almost 1,700 trees, out of the 3,000 evaluated in June, what we found is that after the flight made in June, July, 3 months later, the trees that showed symptoms were in higher proportion those that remote sensing said that were affected. In blue are the true negatives. The true negatives are the ones that became affected or showing symptoms after both pathologists and remote sensing agreed that they were not affected. But every time that we did exactly the same, every time that we did a revisit, we found in an accumulation of the symptomatic percentage, we found that in all cases, the trees that became affected were in higher proportion those that remote sensing was indicating that they were affected. So anyway, can we apply this method to larger areas? Well, we are already doing feasibility analysis, and we know that we can fly the entire buffer zone in about less than 10 days. using this type of same technology and using hyperspectral and imaging spectroscopy. How much of this can be applied or transferred or scaled up to satellite data? Well, we have Sentinel-2 satellite that some of the bands are in the red edge, which are bands that are affected or absorbing chlorophyll concentration by chlorophyll concentration and can be of interest in this context. But now, mind you, that we are talking about spatial resolutions between 10 and 20 meters. So we did, this is a PhD thesis that we are supervising right now, and so it's not finalized work by Alberto Hornero from Cordoba, but this is the fields in the hyperspectral, and this is the corresponding Sentinel-2 data that we get every 10 days over the same site. And because we had the field data collected and also the hyperspectral data, we could evaluate the performance of indicators from Sentinel as compared to hyperspectral and also as compared to the field data. By looking at 2016 summer, 2016 Sentinel and 2017 Sentinel, I mean 1 year difference, we could calculate the percentage change, I'm finishing, we can calculate the percentage change of the vegetation index from Sentinel, and by this calculation for all the fields that were evaluated, we got some results that I believe are promising, because when we compare the Sentinel percentage change against the percentage change in the incidence, we are getting some good results, which brings light regarding the potential use of these methodologies, not for pre-visual detection, but for the monitoring of affected areas once we know that an area is affected. So I finalize with some conclusions, just some take-home messages that I think are of interest. High-resolution airborne hyperspectral and thermal remote sensing traits detect Xylella fastidiosa symptoms at early stages. And I think that we can claim that not only at early stages, but even at pre-visual stages, the asymptomatic trees detected by remote sensing, asymptomatic, were more likely to develop symptoms than the remaining asymptomatic population. So I think that we are really getting into the pre-visual. The disease incidence detection was successful, yielding over 90% precision for the affected trees, obtaining overall accuracies of over 80% from a 2-year data set with more than 7,000 trees inspected and scanned using imaging spectroscopy. And finally, Sentinel-2 images were successfully related to percentage change incidence. I think this is of interest for the future potential monitoring of affected areas. Obviously, this is not my work. This is the work of several people from CNR, from the University of Bari, from the Experimental Research Center of Basile Caramia in Loco Rotondo, from CSIC in Cordoba, JRC, Peter Beck and I are coordinating these campaigns and all this remote sensing work, and also some external collaborators from the University of Swansea in the UK and the Karlsruhe Institute of Technology in Germany regarding the modeling versions and some of the methodologies for the hybrid approaches. And that will be all. Thank you.
Okay, thank you, Pablo. Our next speaker is Ana Maria Diongia from CIHEAM in Bari. And Ana Maria is going to talk about the canopy distribution of Xylella in the Apulian olive cultivars.
Thanks, of course, to the organizers for the good job in organizing this event, and especially the local ones. And, well, my presentation is focusing mostly on distribution, the canopy, aimed at defining a good sampling method. So, was fitting more in the previous session. But anyway, what Pablo said, by remote sensing approach, anyway, you identify suspected trees which are symptomatic, but then inspectors has to go there and check. So how to check is my job, the ground truth. Okay, so we combine both. And sampling. Well, sampling is usually a very crucial rule. We already saw before in the consignments, because Maria Vlami showed that we have already international standards, phytosanitary standards, which are focusing on statistical-based methods for sampling at consignment level. But very not knowledge, I should say, is about sampling with statistically based at the grove level, and especially for olive trees. So, of course, the sampling method is also supporting studies for infection dynamics of the pathogen. So by now, based on the Apple phytosanitary standards for sampling and detection, of course, if we have symptoms, no doubt, so we have to collect from symptomatic trees. And in a way that we have, of course, to collect twigs which are having leaves with symptoms or close to symptomatic part of the branch. And, but what about asymptomatic olive trees? In olive trees, usually for asymptomatic sampling on plants, we refer to the distribution of, which is an even distribution of the pathogen on the canopy. So we try to take a sample which is representative of the canopy. Now, focusing on olive trees, in reality, looking to the symptoms, we have evidence that symptoms are mainly concentrated in the medium upper part of the canopy. In Apulian case, And so the indication was to collect as much as was possible for asymptomatic trees from that part of the canopy in order to get the infection for detection. Now, as I said, I'm focusing on the activity as a preliminary results of Task 4.2 in WP4, which is focusing on implementing sampling monitoring procedures, and referring to the subtask 3, which is focusing on development of appropriate sampling procedures for olive groves. And so not at the consignment. So the canopy, the knowledge on the canopy distribution of Xylella is important because of, before to set up a sampling method for the olive grove. So we identify an olive grove in the infected zone of Apulia based on a demarcated area, which is the official demarcated area, which is showing close to the really the outbreak, the first outbreak in Lecce province, and the grove was chosen because it's irrigated, properly managed, so the trees are well managed, and about 174 olive trees of different cultivars, over 50 years old, and we have represented Sellina di Nardò, Frantoio, Cima di Melfi, and Leccino. Now, the geolocalization has been made of the trees by the use of Xylella, which is an application designed and developed by CIHEAM Bari, and which is also in the same VP under implementation for European use. And so in March 2017, we make the assessment of the infection of the grove, and just to see the distribution of the cultivars in this field. So we have different colors for different cultivars, and the detection was made by using the direct tissue blot immunoassay, which is a serological method included with as a real-time lamp in the EPO phytosanitary measure protocol for Xylella, and the negative by DTBA were processed by real-time lamp as a molecular detection. And I'm not spending much time on both techniques, but just to highlight that these techniques were set up in order to avoid the movement of infected plant material insect vectors, as was already said by Tayasin, relatively to real-time lamp. But for DTBA, it's very interesting that of course, you don't do on-site the DTBA, but at least you print the membranes on-site, and then you can process in the laboratory without taking plant material. Anyway, this method was used instead of the serological method of the ELISA in order to make different prints with the twigs and see more carefully the presence of the infection at different sections. And real-time lamp, which was already explained by my colleague in the previous section. Now, concerning the infection status of the grove, we have the Gelina Nardò, Cima di Melfi were showing the highest values, but also Lecino and Frantoio were highly infected. We can say that an average of 16, more or less 9% of infection rate, and the high rate of infection was in all cultivars, so regardless susceptibility, because we know the Lecino is less susceptible as the Frantoio, and the infection pattern regardless to the cultivars. So we decided to choose Gelina di Nardò as the most susceptible and Lecino, taking 5 plants, and based on the absence of symptoms or infected plants, of course, but very low symptomatic, I mean mild symptoms or asymptomatic. So the sampling scheme was made in half canopy, as divided in 3 levels, and we were taking twigs from each level, 4 twigs per level, and we divided the twigs in 3 portions as apical, medium, and basal portion, in order to understand really the localization of the infection. And then, of course, the detection was made was not a quantitative detection, but just to see if there was a presence or not of the infection. And by ANOVA test, we, of course, had a result, which is, of course, a significant difference between the Gelina di Nardò and Lecino, which was already known by previous observations, so which is a very significant difference. And but what is I want to focus the attention is on Xylella distribution at the canopy levels in the 2 time intervals. So one was based in May, and one was based, as intervals, and one in July. So spring and summer. And we saw that no differences was in Gelina di Nardò, because the distribution of the infection is homogeneous on the canopy, but a big difference is among the levels of the infection at the first level for Lecino, which is the less susceptible, compared to the other levels, which are, so the L1 is the lower level. And this is also clear separation by ANOVA test, factorial ANOVA test, that is showing the differences, a significant difference. And this result, even if it's preliminary, of course, we are going to repeat this approach next year with the same, we will going to retest with the same approach on Lecino. We will not retest anymore Gelina di Nardò because it's homogeneously distributed in the canopy, but we will include the Frantoio, which was one of also in the same field of the low susceptible cultivars. So this is, as I said, there could be a preliminary results which provide a useful indication for sampling tree canopy in asymptomatic tolerant olive cultivars. And now, as the twig portions, we didn't, in the 2 time intervals, in spring and summer collection time, we didn't find any significant difference. So showing that the 20 centimeter twigs that we already have as a protocol for sampling is enough for detecting without any preference of the twig portion. The only things, of course, we have to be sure that contain also mature leaves. And so the sampling method in olive groves is ongoing activity. We selected 32 olive groves in the containment area and buffer area of New Foci with low infection rates, so less than 5%, mainly of tolerant cultivars, so Lecino and Frantoio, and showing mild or no symptoms. This is we are going to in order to set up a sampling scheme which is efficient at the grove level, we are going to put, of course, the different grove as shape, plants, and the different sampling schemes as one of the input for special characteristics sampling schemes. And one input will be the assessment of the infection status of these 32 olive groves as a second input. The third input, the spatial patterns of Xylella infected plants, processing by spatial analysis by distance indices. And everything will be, of course, processed and I should say reduced error in the sampling and more confidence level, precision, accuracy will be, of course, achieved in a sampling method by processing in MATLAB environment. And so this will be the activity that is already ongoing and is going to be concluded the next year, so with a sampling method statistically based for the olive groves of asymptomatic or tolerant cultivars. And I thank the team for this. I was trying.
Perfect, thank you. Our next speaker is Juan Navas, who's going to talk about the spatial and temporal dynamics in orchards in Puglia.
Okay, thank you very much. I would like to acknowledge the organizer for gave us this opportunity to present this work in this as an oral presentation in this conference, and I will want to present the results of work, a collaborative work between two main institutions, our institute in Cordoba, southern Spain, and the CNR in Bari, and dealing with the spatial and temporal dynamics of the olive quid decline in different orchards in southern Italy. As we are here in a, let's say, heterogeneous audience, I decided to start with the definition of an epidemic, because many times when we think in an epidemic, we forgot that can be either a temporal progression, but also has a spatial component. So when we are talking about epidemics, we have disease progress in time, also disease gradients that will be addressed in other presentations today or tomorrow, and also has a spatial component. And we apply spatial analysis to disease data. We are basically trying to answer a question: how far we are from a random, regular, or cluster distribution. So this is the main objective of a spatial pattern, let's say, in a basic way. So the spatio-temporal dynamics of Xylella diseases have been addressed before in different pathosystems, particularly in the citrus variegated chlorosis in Brazil basically by the group of Chico Laranjeira in different areas in Brazil, and they conclude that the contribution to the new foci in a given field was due to infection inside the tree, inside the plot by the different vectors. Also has been addressed for hormone leaf scourge in the US, in California, and they found very interesting results regarding that depending on the genotype of the bacteria, you can have a cluster pattern or a random pattern. That is, according to this author, will be related with the different susceptibility to this particular genotype to the cultivar present in the field. So now the main objective of our work was to assess the spatio-temporal dynamics of the olive quid decline syndrome in southern Italy, and this is included in one more broader objective within the Ponte project that deals with the field surveillance system for vector and disease monitoring. Pablo has showed the result from the remote sensing work, and we use the same experimental plots to determine this spatio-temporal distribution. So we use these three areas that have already described in the infected zone, and we select about 16 different plots 8 of them were monitored from almost every 2-3 months, so five times between June 2016 till July 2017. With this information, as Pablo mentioned, we estimated the disease severity in each single tree of the different plots at all these 5 disease assessment dates, using this scale from asymptomatic trees to death trees, from different degrees of severity. One was only when we observed a symptomatic branch, then 2, 3, and 4 when the relative area of the canopy were becoming symptomatic with the typical decline symptoms. So this is just to give an idea of the initial position of the situation of the different plots we selected. So we select a range of different disease incidents in the first time, from nearly no disease to almost all, more than 90% symptomatic trees, but also with a range of disease severity in each single plot, from almost very, very low severity to mid severity, and also with a range in the size of the different plots, from 36 trees to more than 500 trees. So just to account for different initial situations in which we could study the spatio-temporal dynamic. This is a first overview of the results. In this panel is represented the disease incidence, that is the percentage of affected trees, independently of the quantity of the disease they show. And here you have the disease severity in this scale from 0, no symptoms, to 5 death trees. As you can see, there is a progression in both parameters, particularly in disease incidence, but also in disease severity on time. So on average, in this 1-year study, we have an increase that range from 17 to more than 60% in disease incidence, with an average of 43% in disease incidence, and in disease severity from 1.6 to 2.4. So on average, an increase in all the different plots, or more than 1 point. So there is a continuous increase in both disease incidence and disease severity. And we apply the study analysis that was already mentioned in the previous presentation. And just to, I will not go into the mathematical details of this analysis, because it's a bit complicated, but just I will tell you that you can, when you use the original data, in this case we are using disease severity, because this analysis was developed for counts. You classify the plants into different classes: patches and gaps. The patches are those areas in the field that are obviously more affected and can spread the disease, and the gaps that are low affected or no affected and are more likely to receive or to become affected. The best thing is that you can calculate an index of aggregation that gives you this initial objective to classify your plot into random or aggregated distribution, but also you can quantify the number of clusters and the area occupied by each type of cluster, and with different probabilities. That is the meaning of the different colors. In red colors are the different probabilities that a particular tree becomes to the patch, or in the green colors to a gap. So with this analysis you can classify the plants, as I already said, but also you can apply an spatio-temporal association test, so you can compare statistically two consecutive assessments or two assessments that have the same coordinates. So this is just an overview of some of the results in which we obtain for the different plots, either aggregated or non-aggregated distribution, but on average, we obtain a regular distribution of about 25% of the plots, a non-aggregated on 44, and aggregated distribution in 31% of the plots at the initial stage in June 2016. Again, this is the figures I presented before, and I have selected some of the plots because we have no time to describe every single plot. So this is how we proceed. This is the observed data on disease severity for this particular plot that belongs, was grown with cultivar Xylella di Nardó that is considered susceptible to Xylella infection. And here you have the map obtained through the SADI analysis. In this case, if we compare with the next assessment, compare the assessment in July and October, 3 months later, we can see where appear the new symptomatic trees. This is just an image of the observed data, and here you have the two SADI maps for the two assessments. In both cases are significantly aggregated. You have an aggregated pattern, and in these 3 months you have an increase in severity here of 26%, and in incidence an increase in severity of 0.6 in a 0.5 scale. So in just 3 months you have this increase that we saw on average in the previous picture. So one, in my opinion, very useful tool of study analysis is that you can compare statistically two consecutive maps of disease presence. And here you have the comparison, the statistical comparison between two consecutive assessments, and in the pink color are those areas where there is no agreement, so there is a change in the two assessments, but in the red colors and yellow, you have those areas where the status of the plants are the same in both cases. So the conclusion is that both those maps are significantly associated, so these foci are connected with the previous one. So there is an increase, mainly an increase in the size of the cluster, but more than in the number of the cluster. So this is an example for another cultivar, the Apulian, now on the 5 disease assessment from July to July in 1 year time. And here you can see how disease progress in disease incidence from 30% to almost 100%, and in disease severity from 0.5 to 2.5. This is a clear, common picture of the progression in the different plots when we have a susceptible cultivar. Here you have the different maps. In most cases, you obtain a significantly aggregated pattern in these plots. And if you estimate the number of patches and the size of the patches, there is an increase in time, and also you can compare statistically the different disease assessment in this matrix. So in many cases, 2 consecutive disease assessments are significantly associated, so we can conclude that the new disease foci often appears close to previous foci, suggesting a secondary spread by vectors. This is a different case for cultivar lechino, considered tolerant. Here you can see the increase in disease incidence and disease severity. From July to 16, you have 28% disease incidence and 0.3 severity. At the end, you have 70% disease incidence, but on about 1 value for disease severity. So it remains almost constant till the last disease assessment in both cases, incidence and severity. So we have to look carefully to what happens with these plots in the future. If we go back or continuous increase, you have here the same figures for the different plots, and in this case were associated but not statistically. So maybe there is more components that are regulating the spread of the disease in this particular cultivar, and not only the original foci that are present in the field. This is another example for also a mixture of both two susceptible cultivars, the same situation, also association, particularly into consecutive disease assessment, but not when we go further. To summarize, we have an initial situation with a variety of spatial pattern in the different plots, and at the end, some changes, other not change, but three very simple messages to finish. The initial disease foci determine the spatial pattern in most of the plots. As I said before, the new disease foci often appears close to the previous foci, suggesting this secondary spread. And aggregated spatial pattern is mostly dominant, as is expected for a vector-borne transmitted disease. I just want to finish, acknowledge the financial support, the Ponte project, and all the people that participate in the work, and that most of them are present in the audience. So thank you very much.
Thank you, Juan. Next we have Antonio Vincent, who's going to talk about insights into the spatial-temporal spread of Xylella in southeastern Italy.
Okay, so first I would like to thank to the organizers, especially EFSA, for selecting this talk in the oral session, and also special thanks to the Universitat de les Illes Balears that is hosting us during these days, and also for the students that are helping with the organization. So this is the work by my PhD student, Joaquín Martínez Minaya, and also together with David Conesa and Antonio López Quiles. They are professors in the School of Mathematics in Valencia, and also co-supervisors of this PhD thesis. Maria Saponari, who is the coordinator of the X-Factor project, and myself from IVIA. So that was more or less 1 year ago when most of the people that are here, we met in Bari in the kickoff meeting of the X-Factor project. And to me it was a kind of really shocking experience to see the devastation of the disease in Apulia, and it was the starting point of this work. So the objective of this study is still a preliminary study that we are going to show some data, is to estimate the probability of the occurrence of Xylella fastidiosa in southeastern Italy based on climatic variables and spatial factors. And to translate a little bit is to better understand the role of climate and the spatial dependency in Xylella fastidiosa spread. So previous talks have been dealing with the spread of the disease at plot level, at orchard level, and here we are going to try to see this spatial effect at more regional, larger scale. So the first is the data that we need, or that we have, is first the response variable, presence or absence of the Xylella fastidiosa, based on the official surveys that were the plant health officials of the region of Apulia, who kindly provided this data to the X-Factor and Ponte project to work on it. And well, you see that the surveys efforts have been a really massive survey in the area. These are only for 2013 and 2014. But one thing that is interesting to us before starting any modeling effort is to see how these data were, let's say, obtained. So if there's some aggregation in the pattern of the survey, there can be also influence in the model, and we need to look at this before start to work on it. And you see that in 2015, the survey effort was more localized in the front of the expansion of the disease, and for 2016, most of this area was almost, I think, every orchard was surveyed there. And okay, this is one animation that my student kindly prepared, and you can see here how the days are passing and how the dots are obviously in green the disease absence, and in red the disease presence. and I think we are going close to the end. Now we still have to see the buffer zone, but you see how there is some heterogeneity in the survey strategy. So we decided to focus only in the data from the south of the Salento Peninsula in Lecce province. That you see that the survey for this 2013-2014 period was more regular, and this for us is better to do the modeling work. So what are the covariates that we include in the model? One obviously is the spatial distribution of the data, so the coordinates of the data. But we need to look also at the climate. That is one of the points that we wanted to see, the influence on the disease. For this, there is this, probably most of you know, the WorldClim database is an open database for climate data that can provide the monthly average data from the period of 2050 to 2000 at this resolution that is about 1 kilometer per 1 kilometer. So it's a very high resolution. Obviously, it's by interpolation, but it's a very good resolution. And these are the set of different bioclimatic variables that are in the data set, and you can just download and use in your models. Before going to the numbers, so we did some descriptive analysis. This is a Copenhagen classification based on the criteria of PIL that they updated this Copenhagen classification, that is very old classification. And if you just look at the south in the Lecce province, you see that is in yellow. The CSIC is the typical Mediterranean climate with dry summer and cold winter. So and all the provinces in the same color. So this is not really useful for modeling. So also we, based on the temperature data, the minimum temperature in winter, we applied the thresholds developed by Professor Purcell many years ago for the pest disease in United States, and although it cannot be extrapolated directly to this situation in Puglia, but it's a starting point. But again, we see that all this area of Lecce is in red, so again, for modeling, it's not very useful to have this very uniform. So finally, we decided to use the data itself, so using the minimum winter temperature that is somehow related with the survival of the pathogen during winter, and also the other indexes of temperature more related, let's say, with the development of the disease after the overwintering. So the mean temperature from April to October, or the accumulated degree days for the same period. So this is some descriptive analysis for these variables. You see, again, for the 2013-2014 period, and although it's represented all the Apulia region, these box plots are only for the Lecce province. And you see again in green the absence, and in red the presence, and this is how the values can range. And although the box plots are not so much different, we can see that when we look at the median value of the box plot, it seems to be a bit higher in the affected grid cells compared to the absence. And we'll see later that this has an influence in the model. The same description for the mean temperature for October and April-October, sorry. And the accumulated degree days, I forgot to indicate that the temperature base was 15 degrees. That, well, discussing with the expert on the bacteria and the disease, it was kind of threshold for the development of the bacterium and the disease, but obviously we can play with other temperature thresholds. So the inference that we use is Bayesian inference, and I don't want to go deep into the question, but this is the Bayes theorem, and there is a fundamental difference from the frequentist approach that is widely used for most of us. In the frequentist approach, we only use the data, but in the Bayesian approach, we can also integrate some prior distribution, prior information that we have from expert knowledge or from previous experiments, whatever, okay? And from these two things, we can obtain the posterior distribution. The advantages is we can include this expert knowledge, that this is not our case because we used non-informative priors. So that means that the outcome will be very similar to the frequentist approach. But then there is another advantage, is that we can fit complex models, as the model that we are going to see now. And this is a great advantage compared with the frequentist approach. Again, also, the advantage is we can get the whole distribution, the posterior distribution, not only an estimate of the mean value of the parameters. So that means that we can interpret in terms of confidence credible intervals and not in confidence intervals. But the problem is we need to find an expression for this posterior distribution, and we need to use simulation. This is the standard approach to do simulation in Bayesian inference. This is to use the MCMC, Markov chain Monte Carlo methods. The standard software is the Winbugs. There's many people doing modeling using this software. It's also open data software, but it needs a lot of computation power, and especially for these spatial data sets that you are dealing with thousands and thousands of grids, sometimes you need real, very powerful computers. So the approach that we used is this method that is INRA. Is the acronym of Integrated Nested Laplace Approximation, was developed by Harvard in Norway some years ago, and it's a much more efficient simulation tool compared with the MCMC, and especially for this spatial data set with a high number of grids, it's much more efficient. Well, this is the model. Again, I don't want to go into details, but this is just a logistic regression where we have the covariates that are the climatic covariates, and this W is the spatial factor that in this case was a geostatistical term, okay? Here you have information about the hyperparameters, whatever. I'm not going to explain this now. So these are the different models that we fit to the data. And these are the two statistical indexes that we use to compare which model is better, okay? So this WAIC is the Watanabe-Keiki information criteria, is an index for, let's say, measuring the quality of model fit, okay, how the model fits to the data. And this LCPO is to measure, let's say, the quality of the prediction. And as lower is the value of these indexes, the best is the model, okay? So we see this is the null model without any kind of covariate, and these are the values for these indexes. And you see that these values of the indexes are somehow reduced as we integrate in the model T-mean, accumulated degree days, a combination of the different climatic covariates. But I think there is some, okay, here. The strong effect that we see in reducing the values of these indexes are when we integrate this W, that remember that is the spatial term of the model. And we can see that is a reduction by hundreds. So that means that although the model is still keeping the T-mean as a covariate, the strongest effect in the model is related with the spatial component. These are the values for the mean of the posterior distribution for the parameters. Just to look at T-mean, that has a positive mean of the posterior distribution. That means that the T-mean higher minimum temperatures in winter are related with higher probability of presence of Xylella fastidiosa in the data set. Okay? So these are the outcomes of the model. This is the mean prediction, the probabilities from 0 to 1. We are working with logistic regression, and this is a very interesting feature of the Bayesian inference that we can get also, because we have the full posterior distribution, we can also calculate the standard deviation of this prediction and then get an information about the uncertainty of the prediction, not only having the mean value. So you see from 0 to 1 in different colors, the prediction and also the uncertainty associated to this prediction. So another step that we did is, okay, we used the 2013-2014 data, that is this data set, about 200-something presence and about 4,000 absences with this prevalence of 5.3%. But the idea is to see how this model is able to predict what will happen in the future. And for this, we used the data set of 2013 and 2016. And also you see the characteristic, in this case, a much higher number of cells, grids that were surveyed, but the prevalence was somehow similar, a bit higher, but still in a low prevalence. And this is the outcome of this evaluation with a ROC curve, that is the receiver operating characteristic curve. Basically, it's a measure of the specificity and the sensitivity. So if we see the good things, that there is a true positive rate of 73% and a true negative rate of 81%, but if we look in the opposite side, we were not able to predict correctly 27% of the positive, so that is the first negative rate, and nearly 20% of the negative were also not well predicted. So that means that the model needs further improvement. So to conclude, as the previous speakers already said, at orchard level, so at regional level, we also can conclude that the spatial effect had the strongest influence in Xylella fastidiosa occurrence in this Lecce area. And also higher probability of Xylella fastidiosa occurrence with increasing winter minimum temperature. And these are some ongoing works that we are doing with new climatic data tests from the colleagues of the JRC. They have more recent data, the colleagues of the CMCC, and also to include a temporal effect in the model and using other spatial models. And this is just to show you that now we have the problem in our own region, and our plant health officials are also doing surveys on this, in this case, if the almond leaf spot disease, and also we hope that next year that we meet, we can present some modeling work on this problem. And just to thank our funding project, Spontaneous X Factor, and thanks to all of you for attention.
Thank you, Todi. Our final speaker is Samuel Soubeyrand from INRA, and he will be talking about estimating the dynamics of Xylella based on the French surveillance data.
Thank you. Okay, I will indeed talk about modeling and estimation of the dynamics of Xylella fastidiosa based on French data, and be patient, I will give an estimate of the introduction date at the end of my talk. And you will see that the emergence is probably, in France, is probably not a recent story. So in 2015, Xylella has been was detected in situ in Corsica, and the stratified surveillance was settled and data were centralized. There is a poster about this data, the poster of Pauline de Gerfagnon, to see more details about this data. And 2 years later, we have about more than 20,000 analyzed samples, about 6% of positives in Corsica, 2% in Paca. So Paca is this region. Okay. And our aim was to infer the dynamics of Xylella fastidiosa with a mechanistic statistical approach that handled the specificities of the surveillance-based observation process. In this approach, we acknowledge the difference between the dynamics of the detection and the dynamics of the disease, and we try to understand what happens. So if we look at the dynamics of the detection, okay, here you have the raw data, and you have, with the solid line, the percentage of positive cases across time. So, and you see a decrease, which is even more visible for symptomatic plants. Okay? But what does this decrease mean? It could be a decrease of the actual disease prevalence, okay, in the overall host population, because detected infected plants are destroyed. But it could also be the signature of a sampling strategy that varies in time. Indeed, to assess the global situation in Corsica, more and more host genera and more host municipalities have been surveyed. Okay, And so the preference in sampling at-risk hosts might have decreased with time. And our approach tried to disentangle this situation and understand which of this explanation is the most influential on the raw data. In addition, as you know, so Xylella is a multi-host pathogen, and in Corsica, it is in an environment which is quite complex with many host species, which are quite fragmented host populations with wild, urban, and agricultural areas. And so we can suppose that there are several hosts that can be infected. Some are infected, some are healthy, some are asymptomatic, some are symptomatic. But importantly, we could also imagine that only a part of the whole host population could be observable, okay? And the understanding of the pathogen dynamics may be complicated by the existence of a hidden compartment in the host population, which may play the role of an infection reservoir. And so we built several competing models which are based on a susceptible, infected, removed architecture. And in these models, we concentrated on two specificities. First, the hidden compartment component of the model. In some of the models, there was no hidden compartment, and in other models, there was a fraction of the whole population which was hidden, and this fraction, we estimated this fraction. And concerning the preference in sampling, we consider three options. In the first option, sampling is uniformly random across the whole host population. In the second option, there is a preference for sampling at-risk hosts, okay, but this preference is constant in time. And in the third option, there is also a preference in sampling at-risk hosts, but this preference varies in time, okay? And so to estimate the parameters of these models, we applied a Bayesian inference approach using an MCMC algorithm, and we estimate the model parameters based on the based on the monthly counts of infected, healthy, symptomatic, asymptomatic plants. And we made model selection with several statistical criteria, for example, BIC, DIC, and base factor. And what we saw is that we couldn't two models were good. well, we couldn't separate the goodness of fit of the two best models. And so these two best models are here. So in both models, the preference in sampling corresponds to the third option. So there is a preference in sampling at-risk host, and this preference is varying in time. But in the first model, there was no hidden compartment, whereas in the second model, there was a hidden compartment corresponding to, a priori, a large fraction of the host population. Okay. And before commenting this graph, I will explain what are these graphs. So here you have, under the first model, selected model, you have some output, and under the second selected model, you have the other output. And in the first panel, you can see the inferred disease dynamics, okay? You remember that the observed disease dynamics is this. Well, it's not the disease dynamics, okay? It's the detection dynamics. But here we infer the disease dynamics, and you see a growth of the disease up to the first up to the detection time, which is here 0. Okay? And here it's in the whole host population. Here it's in the observable compartment. And the third panel corresponds to the hidden compartment. Of course, in the first row, there is no hidden compartment since we work under the model without hidden compartment. And in the second row, you have a dynamic in the hidden compartment. And the histogram that you see here is a posterior distribution of the introduction date. So what we see is that in the first scenario, so under the model without hidden compartment, there is a quite low prevalence of the disease, and we estimate the introduction around 2001. Whereas in the second scenario with hidden compartment, there is a larger prevalence of the disease, and the introduction is dated at about 1985. And now the implications for the future. Here we consider that there is a constant but reinforced surveillance effort and a constant preference in sampling. Under the first model, without hidden compartments, it seems that the surveillance could decrease the overall prevalence and allow Xylella fastidiosa eradication. Okay, so we see the decrease here, which means eradication. In the second scenario, the hidden here you have to see the hidden. You have to read the hidden compartment does play the role of an infection reservoir and makes the control difficult. Okay, we can see here that, well, despite the surveillance, the disease continues to grow. So to conclude, our work opens a scientific debate about the introduction date and the prevalence of Xylella fastidiosa in Corsica. And we need to apply, of course, complementary approaches using more data and using other kinds of data, for example, genetic data. And one of the examples of this alternative approaches is given in the poster of Candy Aboud, who try to fit spatial-temporal models to surveillance data. You saw that we have two scenarios, and actually today there are pieces of evidence in support of the second scenario with an introduction around 1985 and the hidden compartment. Indeed, Marie-Agnès Jacques and her colleagues applied a phylogenetic approach to estimate the mean dates of molecular divergence between French and American isolates. And they obtained these dates of divergence, 1980 for strain ST6 and 1965 for strain ST7. These dates can be viewed as proxy or lower bounds of the introduction date. And they are more consistent with our second scenario, which infer an earlier introduction date. Then we have some colleagues at INRA, Astrid Cruot, Jean-Yves Plus, and their colleagues, who are interested in the insect and the prevalence of Xylella within the insect. And actually, they sampled some cystus in Corsica, and the percentage of Xylella fastidiosa positives philenus sampled from this cystus was about 20%. Okay? And cystus is actually a plant which has been sampled in Corsica, but the number of samples is quite moderate compared to the huge abundance of cystus in Corsica, especially in the wild. Okay? And so cystus could contribute to the hidden compartment hypothesis. Thank you for your attention.
Okay, thank you, Samuel, and thank you to all the speakers. We have about 30 minutes for discussion, so who would like to begin?
I have a question for Antonio Vicente. You found a high significance of the spatial effect in your model. Is it because the disease started at a certain location and it is still expanding its range? And if this is true, is it reliable to base the model also on climatic factors of the current range of the disease?
The model itself was fit to a data set that it doesn't have a temporal component. So for the model, all the data are only spatial coordinates. As you saw in the last slide, the way to improve the model is to include a temporal component that will take into account, as you said, this further spread of the disease. But this is just a preliminary evaluation. And yes, the climate for the model should be the climate that is associated to the data set. So, and you see that we are not using this model to extrapolate to other regions. This is another kind of modeling work that needs other different approaches. But what is true is that the work limb is from 1950 to 2000. So obviously the epidemic probably started much later than 2000. So this is because now we are improving with more recent climatic data sets from Jersey, from the CMCC that is a partner of the project to have climatic data that are for the time period where the epidemic was developing.
I had a question about the remote sensing. Can you now have the software or informatics to transfer your data automatically to a map? In other words, like the dots, the grid of dots that some of the other printed examples of. Can you generate these automatically? And by the way, I'm particularly impressed by this session, by not only the findings that each of you contributed, but the progression in which the talks were arranged. That worked out great.
Well, thank you. Regarding the remote sensing data, it depends very much on the type of cameras that we operate. To give you an example, the last year, the thermal camera was processed automatically, and in less than 24 hours, the full mosaics of thermal data were available for the field crews to make decisions regarding the sampling strategies and to go to the field to specific orchards and to decide if there were specific hot spots and so on. So the processing of the imagery it's very much automatic or semi-automatic. Thermal data, it's processed normally in less than 24 hours, in just a few hours, for several thousands of hectares at a very high resolution. I'm talking about 40, 50 centimeters. For the RGB and color infrared, it's a fully automatic methods. With the software, we just put all the images and all the data that has been recorded during the flight, and it's a fully automatic method. The data that takes a bit longer is the hyperspectral, because it's heavier regarding computationally speaking, and normally, depending on the servers that we have available, it's a semi-automatic method that normally takes a few days. With the laboratory, with the right type of technology and personnel, we are talking about a few days maximum between the flight has been carried out and the final results are obtained.
One last thing, I'm also struck by the contrast between model outputs, which are basically graphs and numbers, versus a video of what's happening. Because we humans are pretty good with understanding what we're seeing in terms of an image. Sometimes it's a mistake, but we reach those conclusions very, very quickly and easily. So I think both types of approaches have their value. But the ones where the average man on the street can understand, looking at that, how that disease spreads over time, they can see what's going on.
Sure, and one of the issues that I think that I like to remind regarding remote sensing is that I wouldn't say that remote sensing is useless without field data, but all the remote sensing approaches and methods that we use, they fully required field assessments, not only for calibration, but also for assessment of the products and the model retrievals that we carry out. There's always, especially when very high resolution data has been acquired, that we go to individual trees to evaluate if the outputs and the retrievals of the plant traits are related to what we actually see at the leaf level or at the canopy level in the field. Without that, I think it's an exercise that is expensive in some cases, depending on the areas that are flown, and without all the ingredients needed in order to make good conclusions. So I think it's extremely important that we understand that remote sensing is not the solution for absolutely everything. It helps. I think it's a good way if we apply physically based and physiologically based methods to retrieve interesting and important information, but it's not flying by flying, because otherwise I think it's we don't do things in a careful way, and I think it's quite important to check that everything is done at the field level, but also in the laboratory correctly in order to quantify and to obtain the products in a good way.
I have a question for Juan Navas-Cortés. You showed that the index of association in the Lecchino cultivar is not significant. Could it be that possibly is the secondary spread in Lecchino cultivar that can affect this different disease progression in the cultivar Lecchino?
Yes, this is a possibility. But we are using a very strict criteria to determine when an association test is significant. It's 0.025. That is usually lower than is commonly used. So at this, the common level of significance of 0.05, also some of the assessment dates are also significantly correlated. So, but I decided to use this more conservative criteria, but this could be a good possibility, that the lower concentration of the bacteria, that it seems to be the major effect of the tolerance of the cultivar, could also affect the transmission rate or the success of the transmission or other factors. But we have to look what happens in the next year, in the next assessment with this cultivar, because they are really interesting results, and this could be one of the reasons.
I have a question for Antonio Vicente. Your model already takes into account the spatial pattern, but I wonder if it's possible to implement in some way in your model, I'm not an expert at all, also landscape fragmentation. I mean, in the case of olive, the epidemiology seems to be strongly based on olive-to-olive transmission. So, if you are dealing with a surface which is entirely covered by olive, you have a given effect. But if the landscape is fragmented and the olive groves are not continuous, can you in some way implement this? And then I have a short question to Ana Maria Dongia. Can I go with both, or I stop now?
Okay.
Yeah, do you want to answer, Tony?
Yeah, so this is the reason because we focused on this, let's say, province, because it seems that it's a kind of cover of olive everywhere, and you remember the dots, it's a kind of regular sampling, so almost all the grids were sampled. If you see above, there is this, as you said, aggregation, there is fragmentation, some areas were not surveyed because probably the hosts were not present. And this is something that for modeling is a challenge. So we are still thinking how to approach this and also to use this data that we use it only for validation, but can be also used to build the model. So I don't have an answer at this moment, but we are busy thinking how to deal with it. Also because in the situation that we have in Alicante is the same. It's affecting almonds, but almonds are not everywhere. So there are some plots, some valleys that have almonds, but others not. And we need to address this for modeling. Yeah.
The short question for Anna Maria Donghia. If I understood well, in Lecino, you found that Xylella is mostly limited to the lower part of the canopy, okay? But at the same time, you said that generally speaking, infection starts from the medium higher part of the canopy. So I'm a little bit confused because
I was starting with the fact that there are guidelines already established at the European a level for survey of Xylella, and also as EPO phytosanitary standards for olive specifically, based on the experience gained up to now, was supposed to be more accurate to sample for the medium upper part of the canopy in asymptomatic plants in order to catch the infection because of the uneven distribution on the canopy. Now, we did this work in order to really do a sampling very as a number, but also as a distribution on the canopy as a sampling, so to make a more accurate sampling and detection of the infection at the different levels. And for Cellina di Nardò, of course, is homogeneously distributed, and we know. But the problem was how to sample tolerant and asymptomatic olive cultivars. And Lecino was showing this prevalence of an infection on the first level, which I think, I'm not an entomologist, perhaps you can help me in this. Perhaps my headache was always why the Philaenus must jump on the top of the canopy and then make injection on the canopy, and instead of jumping from ground to the first level. This is a
I have no answer for that, but I can hypothesize that if you find Xylella mostly limited to the lower part of the canopy, maybe this is because Philaenus mostly inoculated the pathogen on that part of the canopy.
Which is which is also, I think, the jump is shorter and is more, fitting to the Philaenus behavior, perhaps. I don't know. There's an assumption, but this is just an indication for sampling on the plant in a more accurate way for asymptomatic plants.
Yeah, this is also a question for Tony. In your last slide, you showed the future works, and I was missing some future works on the applying these models to the vectors, trying to dig a little bit more on the climatic conditions that drives the vector phenology, even activity, and even the temperature threshold for transmission and so on.
Yeah, so then I suggest to you not to miss the session of tomorrow because my colleagues Stephen White and Doug Chapman from NERD, they will present the work they are doing with more, let's say, mechanistic approach with process-based models where the vector behavior, transmission, etc., is integrated in this approach. So from our side, they are just correlative models that are based on data. And in our case, data are presence or absence of the disease in the tree. So we can speculate about the vector, but obviously we need to do the same approach as we did, data for presence absence of the vectors, if they are infectious or not. This kind of data are not easily available at this spatial resolution.
Right, but if you have the absence presence of the vector, you could use your models as well.
Yeah. The same approach can be done.
Okay, right. Thank you.
It's a question for Samuel Soubeyrand, and the first part may be a bit naive, but with a pathogen like Xylella, with 300 hosts or something like that, and where new hosts are regularly reported, does the hypothesis that there is no hidden compartment make that much sense? And then the second question is, in any case, what kind of data would you need to disentangle between the two best models? So in order, in essence, to decide whether there is a hidden compartment or not, what kind of data would you need?
Well, the hidden compartment can be either some hosts which are missed, okay, and of course, if we do not sample all hosts, of course, the hidden compartment is obvious, okay? It can be some missed host, but it can be also, for example, some regions which are not sampled. And for example, in Corsica, there are about 30% of wild areas which are like bushes. And if you see sampling in these areas, they are mostly close to roads, okay? And so you can imagine that there are some roads far from the roads, the hidden compartment, and so the infection reservoir could be there. Then concerning the way to try to disentangle between the two hypotheses, I think that there are some, this study about cystus, okay, around cystus and the insect vectors which have been sampled on cystus, which can contribute to say that maybe the second hypothesis is more relevant. And I guess that an extensive study of this host species, this host genera, in areas which have not been sampled yet could be interesting. If you look precisely at the figures that François Poliakov gave yesterday, there are about almost 3,000 polygala which have been sampled, okay, and about 500 cystus which have been sampled, whereas cystus is much more abundant in Corsica than polygala.
I think it was Peter, then Mike.
My question is also for Samuel. I thought that was a very fascinating study. And I wonder, in your SIR model, maybe I missed it, but in the representation of the landscape, did you assess the role, as you trace back when the epidemic might have originated, have you evaluated long versus short distance dispersal and how that might influence the epidemic and also your tracing back of it?
Okay, so this is only a temporal study. Okay, we only use temporal data, monthly counts of healthy and infected plants in South Corsica, and the model is also only temporal. Okay, but we are working on some spatio-temporal models. Candy Aboud is a PhD student who works on this, and so yes, we will try to introduce long distance disperser, but also several introductions and things like that.
This is also on the hidden reservoir. In one of the first talks on the situation in France, I think Francois Poliakov, unless I wrote the figure down wrongly, said that 80% of the detections were in calicotome. As I understand it, calicotome is also a broom. It might even be synonymous with cytistis.
Was in what? Say it again, just the end.
In calicotome, which is also a broom, known as a broom, and it may also be synonymous with cytistis, which is the species which you mentioned, or the genera you mentioned. So I think the idea of this hidden reservoir is certainly novel and innovative and certainly worth exploring further.
Yeah. Okay.
It wasn't a question, it was just...
Yeah. So thank you for this remark.
Jean-Claude?
Just one comment to Mike. I think there was a confusion between cytisus and cistus. So Mike remarked that, I don't remember which species was also a broom, as cytisus was, but you were talking about cistus, right?
I do.
Okay, we have time for more questions. In the middle.
Also for Samuel, and also about the hidden reservoirs. It seems like you make a case that that's a very strong possibility, that we're looking at a situation with hidden reservoirs. Are current monitoring and control strategies adequate to detect these, or how should they change?
I think that, so as you saw at the beginning of my talk, the strategy for assessing better and better the global situation in Corsica is improving. Okay, but when you do this, when you sample almost everything, you decrease your propensity to sample at-risk hosts, etc. You also decrease your capacity to control the disease. Okay, so there is a kind of trade-off between, but maybe Stefan could speak better about that. Between, in this case, I think in Corsica there is a trade-off between sampling all the compartments of the host population and sampling and eradicating the disease. It's not the same optimum for both. And also there is another issue that I have not evoked, is the sampling of vectors. Okay, some colleagues at INRA claims that sampling vectors more than we do today could be a way to better understand the spatial pattern and also the spatio-temporal the future spatio-temporal pattern of the disease, because vectors can be used as sentinels. And it's especially interesting to sample vector and understand what their role in the infection, because in the epidemics, because my colleagues are able to see when they sequence vectors, they are able to see, of course, which vector they sample, which strain they have if they carry Xylella, but also which host they fit, and so it's really important to understand the network, the ecological network.
Okay, Stephen.
My question's for Juan Navas. So your severity data seductively hints that there may be seasonality in severity. Okay, so there's this little flick at the end. If we make a bold statement and assume that's true, are there plans to try and disentangle what that might be? So is it sort of water stress, or is it from new infections, or is it seasonal predictions from seasonal dynamics from vectors or something like that?
Yeah, we are assessing the disease severity as visual symptoms. We are confident that we really are estimating symptoms due to the disease, to the infection. But in some cases, as you said, could be mixed with some drought stress or some. So the best thing of our work, we are assessing in time. So as much data we have, we will deal with this situation. And if really in a certain point, for instance, in the last assessment made in July, there was a short period, but very high temperature. Maybe this general increase that we observe in most of the plots is due to this maybe mixed effect of the hot temperature at that time. So this is because it would be interesting to see what happens in the future, and as much data and as long we could estimate the disease progress in the different plots, we will solve or will cover for this maybe errors or artifact that we are introducing in a given or a certain assessment.
Are you also looking within the tree as well to look at bacterial levels within the tree, so you can sort of correlate that with
we confirm in all plots in different trees that really the bacteria was infecting the tree.
Yeah,
not in all.
Yeah, so it's more just sort of quantitative bacterial loads within each tree, and then correlate that with severity for that tree.
Yeah, could be nice, but we are assessing 4,000 trees, and this is. Do you
want some help?
Yeah, we applied this same approach for verticillium wilting in olives, and we did that. So we estimate the disease progress in time and space, and we analyze by molecular tools all the trees that were assessed. And also not only if the pathogen was present or not, but also the pathotype, because in verticillium dahlia you have 2 different pathotypes in olives. So in a small plot, you can do that. But obviously, to isolate verticillium is much easier than Xylella. But could be nice if we have enough people or enough resources, we can do that at plot level and really understand how the symptoms and the progress and the spread of the disease is related, for instance, with the level of resistance of the cultivar, the efficiency of the vector, and so on. So, but it's a question of time and persons to work on this.
I think that'd be really worthwhile doing.
Yeah. Okay.
Okay, there's probably time for one more question.
Pablo, you have a model symptomless plants, but you have also data on a severity index from 0 to 5, I think. Have you tried to model this index to quantify this from remote?
Yeah, I only showed one of the parts of the study because we were running out of time, and but we have done exactly the same for different groups of severities, like asymptomatic versus early versus advanced, and also for every single level of severity. And obviously, as more severity levels are included in the model, the overall accuracies and the kappas go down a bit. But we are anyway in the range of, instead of 80% for symptomatic versus asymptomatic, we are in the range of about 70% when we try to model every single severity level. Yes. Yeah. So after we apply the model to every single tree, after we extract all the plant traits from every single tree, then we classify on a tree-by-tree basis. So we give an index of severity for every single tree scanned. So we are talking about several thousand trees, every single classifier.
Okay, I think now we have the poster session, but I'd just like to thank the speakers once again.